So next we'll discuss some classic algorithms as well as challenges with offline RL methods. So let's consider a generic off-policy RL algorithm that we have studied in the class a few lectures ago. So such an algorithm, what it does is that it interacts with the environment using a policy, stores the data in the replay buffer that it collects, and then uses this entire replay buffer to update the policy as well as the queue function if it maintains a queue function, and repeats the whole process. DQN and actor critic algorithms both follow a similar skeleton, but with different design choices for the buffer, for how much data does the buffer contain, what policies contribute to the data set in the buffer, etc. DQN, for instance, maximizes the Bellman error objective, which is shown on the slide, by using data from the replay buffer D. An actor critic method, on the other hand, tries to estimate the value of the current policy in terms of a neural network, so that's q hat pi, and optimizes the policy against this estimated Q function or estimated value for the policy. Now we ask ourselves the question if such off-policy RL algorithms can be applied in the offline RL scenario. So in principle, they can be applied. And to understand why this is the case, let's look at a simple sort of schematic connection between the two settings. So in the off-policy RL setting, where essentially the policy, essentially we execute the policy periodically in the environment, collect data, add it to the buffer, and use the buffer to update the policy. The replay buffer consists of consists of data generated from a mixture of past policies. So imagine a DQN where you have a big replay buffer. It's not just the data coming from the current policy, but a mixture of data from a set of policies that the agent has seen. In the offline RL setting, on the other hand, the replay buffer, it follows a very similar skeleton. And the only difference is that the replay buffer consists of data coming from some unknown policies that the current agent doesn't even have any access to. However, if you look at, or if you recall, the training objectives for training the policy pi in the off-policy setting, a lot of these algorithms, such as Q-learning or actor critic algorithms, do not necessarily use the fact that the data buffer or the replay buffer is coming from the policies generated from a prior instance of the same algorithm. So in a sense, for instance, an actor critic algorithm, it does not really utilize the fact that the policy, the data buffer was coming from the past policy, unlike a policy gradient algorithm, which does utilize this fact. So what we can do then is we can just simply modify these algorithms to do the same training as they were doing in the off-policy setting. However, all of the training is now happening using the offline data buffer, as shown in the octacritic algorithm on the on the bottom left of the slide. So what we'll do next is we'll discuss some classic algorithms which are based on this idea. So a lot of the classic research in offline RL or patch RL has been centered around two kinds of algorithms. One is the kind of algorithm that is sort of like Q-learning style methods, which fit a Q function or utilize it in some manner. And the other sort of broad category of algorithms has been importance sampling algorithms that you have looked at briefly in the policy gradients lecture, but we'll revisit them again. And let's start with the Q-learning style algorithms here. So you've already seen this algorithm, which is called fitted Q iteration. The broad idea behind fitted Q iteration is that you have a big data set, and here the data set can be an offline data set provided to you. So that's indicated as mu in the algorithm. Now what you do is you compute the target values corresponding to the current Q function on all the state action pairs in this data set. So you basically apply the Bellman backup operator, which is equivalent to summing up the current reward with a discounted best guess of the optimal value from the next state onwards. You compute these target values, you store them, let's call them yk, and then what you do is you minimize the Bellman or TD error with respect where you train the Q function to match these target values. And if you do this process over and over again, and if you have enough coverage in your buffer, you are guaranteed to converge to the optimal solution, modulo function approximation, etc. And this is a classic algorithm known as fitted Q iteration. And technically speaking, it's a batch or offline reinforcement learning method. Now imagine if you approximate the Q function using a linear function approximation. What that means is the Q function is equal to some W transpose phi of SA, where phi of SA is a known feature vector given to you, and W is a trainable parameter. In that case, essentially what you're trying to do is you're trying to fit this linear function to the Bellman equation, where you want the Q function to be equal to the instantaneous reward plus the best thing to do from the next state onwards. There are many ways you can solve such a thing. For instance, you can try to find the fixed point of such an equation using in the linear function class. So that's sort of one kind of methods of solving this. You can also try to minimize the gap between the two sides of the equation, which is another set of methods to solve it. And all these sets of methods give rise to a broad spectrum of algorithms that have been utilized in the batch setting. One of the most popular or one of the notable algorithms in this setting is this least squares temporal difference Q-learning algorithm that essentially tries to solve essentially tries to find a fixed point of this equation by using least square solutions. So with a linear function, you can apply the least squares solution because essentially things are you are doing linear regression, and this method tries to do it that way. There's also a lot of literature, some references are provided on the slide, and you should check it out for getting to know more about batch Q-learning algorithms. The second set of algorithms that have been classically studied are these algorithms based on importance sampling. So what we saw in an older policy gradient lecture was that you can estimate the return of a particular policy pi using importance sampling and data from a different or trajectories from a different behavior policy pi beta. So what you do is you simply just sample trajectories from pi beta, but then correct for the returns that you get using the density ratio pi theta tau by pi beta tau. And based on the fact that the policies, or you can kind of decompose this distribution over a trajectory into independent distributions over current actions given the current state, you can estimate, you can write it down as the expression shown in the second line. And turns out that you can always, if you have a batch of data coming from pi beta, which is what we assumed at the beginning, you can compute this expression. You can compute a sampled estimate to this expression by computing these weights, which is the product of the density ratios of pi of a given s, or pi theta of a given s divided by pi beta of a given s in a trajectory, and summing over the return for that trajectory. However, an approximation like this does suffer from a huge variance problem. And so there have been many tricks, including, for instance, only taking into account only taking into account the density ratios from time 0 to the current time step in the trajectory, and so on. And what these methods then typically aim to do is that they aim to sort of estimate the return of a policy pi theta using something like this, using importance sampling, and then they optimize the return of policy pi theta to be able to obtain a better policy, for instance, using policy gradient. There's one other one other kind of methods in this importance sampling class of methods that I would want to go over, which are these methods which are known as doubly robust methods. So what these methods do is that they still do importance sampling, but in addition to importance sampling, they also estimate a Q function, which the Q function tries to is an estimate for the average or the expected long-term discounted return of the policy starting from ST and AT. And what they do now is that they use a combination of both the importance weights as well as the Q function to obtain a low variance but unbiased estimate of the return. And these methods are called doubly robust because they utilize these two things together, like the importance weights as well as the Q function, and more details you should find it in this paper, which is referenced on this slide. Moreover, there are also many other improvements over such methods. It's not just by any means limited to just these three kinds of techniques, but rather there are methods to do variance reduction, as well as methods to sort of build confidence on the estimated values. So can you estimate? Can you give me a high confidence bound on the return? And then what did these methods do is that they try to optimize this high confidence lower bound on the return with respect to the policy using some policy gradient method. So there's a lot of work in this area, and I would really encourage you all to look at some of the references here. But this is another set of broad set of methods. Okay, so now what we'll do is we'll shift into the modern deep reinforcement learning setting, where we would try to see what really happens with when you run deep RL methods in an offline RL scenario. And what we'll do now specifically is we'll collect expert data. So what we'll do is we'll train one of those policies that you guys used for the imitation learning homework, and we'll collect a lot of data from that expert policy. And what we'll try to do now is we'll try to run actor-critic methods, which is sort of reminiscent of the standard or classic FQI or or LSTD style methods that we looked at on this data. So and we'll look at how these methods perform in this setup. So turns out that if you train, for instance, a soft actor critic algorithm on the half cheetah domain, you'll find with expert data, you'll find reward curves that look like the left plot on this figure, where the expected return of the policy that you get as a result is super low. It's like -200. On the other hand, the expert policy on the half cheetah domain gets around 10,000 return. Also, you will find that the Q values here they typically are super large. So the log of the Q values is shown in the figure, and the log of the Q values is +15 or +10, which means that the Q values are 10 to the 20 or 10 to the 50. So what is the average return? The average return is the estimate of how well the policy does, and the Q function is an estimate of how well the algorithm thinks that it is doing, because the Q function is the algorithm's estimate of the return of the policy. So in a sense, what you're seeing here is that the learning diverges, basically. The Q values are super large. We also varied another factor, which is quite interesting here, which is the amount of data that you provide to the algorithm. So if you recall, in supervised learning, we typically expect sort of underfitting and overfitting trade-off, where if you have very limited data, you can exactly fit the data, but you won't generalize. Whereas if you have a lot of data, you might not be able to fit the data because maybe your function class is limited. So what we did here was in order to kind of disentangle the effect of like data limitations, what we did was we trained this agent not only with a fixed data set, but with a data set of varying sizes. So we gave it 1,000 transitions, 10,000 transitions, 100K or 1 million transitions. And in all cases, if overfitting was really an issue, we would have expected a trend that said more data implies higher performance. However, if you see in the curve here, even when you provide it with 1 million samples, which is shown in the red line, the performance is actually not better than 1,000 transitions, which is basically indicating that this issue is not really a classical overfitting issue, which you see in supervised learning. We call this phenomenon, we call this phenomenon policy unlearning, in the sense that you had an expert policy that generated the data, and even behavior cloning on the policy could have worked, but the policy performance that you obtain out of running RL on that data is super low. So in a sense, the RL algorithm has unlearned the policy, and hence the name. So what we'll do next is we'll try to understand what went wrong in this example. And we'll try to kind of formalize that into an exact sort of formal problem that offline RL methods suffer from. So in order to understand deeper into why there's an issue here and why things didn't work, let's look at how the Q function is trained in this scenario. So a standard Q learning style update would update the Q function towards matching target values given by the instantaneous reward plus gamma times the maximum Q value over the next state. It's usually done using a TD error objective as shown on the slide. Now, what actions does the Q function train on here? Meaning that for which actions, which set of actions are you training the Q function QSA or Q network QSA? The answer is you're training the Q function on state actions from the data or state actions sampled from the data. So actions are really coming from the behavior policy on which you're training them. Now, which distribution does the action A prime come from? So A prime is used in the target value where you are taking a max over A prime of the Q function at S prime and A prime to be able to compute regression targets for the Q function. And so which distribution does the action A prime come from? So in order to understand this better, let's sort of visualize the value or the profile of the Q function for a particular state S along the action axis. So the plots that you see here, it's a cartoon that shows the value of QSA on the y-axis as a function of the action on the x-axis, and the state is fixed here. The the dashed line that you see here is the behavior policy. So that's sort of the high density regions of the behavior policy that are marked here. Now, what you see here is that the Q function, it is trained on S and A from the data set. So it's trained on actions that are drawn from the area that lies beneath the, or the area on the x-axis that the dashed curve maps to. Whereas and that's the Q values on the data that you train on. Whereas the Q values at other actions could be erroneously high. So they could be, they're sort of wrong because you're never training on them, and they can be erroneously high. For example, you can have Q values that are much larger than what you've seen on the data at unseen actions. Now, when you do a max over A prime of QS prime A prime, and let's say you can compute the true max here. What kind of actions or A primes would this maximization procedure select? It would end up selecting actions that precisely are erroneously over optimistic. So those actions that are marked with a circle, with a red colored circle there, those actions are the actions that will be used for the backup or for training the Q function. So in a sense, what you're really doing here is you're really querying the Q function at unseen actions, or you're really querying the target Q function at unseen actions, and these and the values of these unseen actions are used for training. However, these values are never trained themselves because you're only training on state action pairs drawn from the dataset. And these actions are not seen in the dataset because these are unseen or out of distribution actions. So in a sense, what's really happening is you have erroneous target values that you're training your Q function with. So you're trying to make the Q function regress to erroneous values. So now we may ask ourselves, why are such erroneous backups such a big deal? And in particular, what we want to ask here is why is this problem so specific to offline RL settings? In that this problem should also happen in online RL settings where the Q function would be erroneously over-optimistic. And you've seen such scenarios. For example, you've seen double DQNs or DQNs to double DQNs. The reason why double DQN was developed was to prevent this erroneous over-optimization problem in Q learning. So why is it really a problem with offline RL? So it turns out that the reason why it's not a big deal in online RL is because when your Q function is erroneously optimistic, you're still allowed to explore you're still allowed to explore the environment, right? And in a lot of the cases, the exploration policy that you use to explore the environment is sort of somehow related to the Q function in that it chooses actions that have high Q values. For instance, Boltzmann exploration or epsilon greedy exploration. And when you do this, you're precisely visiting those actions, or you're precisely taking those actions for which your Q values are erroneously optimistic, and you're observing what the right reward value or what the right value for those actions is. So if you had a Q value that was erroneously plus 1000, you'll take that action and observe that its actual return value is negative 100, and so you will end up correcting your errors using this information. Now, in general, this is not true because error correction may not happen with online data collection everywhere. However, it mostly works fine in practice. Now, the primary ability of error correction via exploration is sort of impossible in offline RL because you don't have any access to the environment. So this problem is sort of highly exacerbated in the offline setup because of no access to the environment. So let's formalize this sort of notion or whatever we have discussed so far into a concrete problem, so as to be able to derive fixes towards this issue. So this problem, I would argue, is a general can be generally or can be abstracted into this term called distributional shift. And the distribution that is shifting here is the distribution is the fact that the behavior policy, which is the policy that collected the data, has a different distribution than the learned policy that you see during training. So imagine you were doing Q learning. Your learned policy is the policy that greedily maximizes the Q function, which is the policy precisely that is used to query the Q function, or query the target Q function. Similarly, if you're doing an actor-critic method, your policy is the policy that is used to take, which is used to again compute the target value here, because you take an expectation under actions drawn from that policy of the target Q function. In both of these cases, both of these policies, the max over A prime or pi, are not equal to the behavior policy, and this is sort of the distribution shift aspect that we talked about. Whereas when you train this Q function, you are just training it with data coming from the behavior policy, and so you're not training on state action pairs drawn from the current policy pi. You're only training on the behavior policy, and hence there's a shift. So to summarize, offline Q learning algorithms can end up overestimating the value of unseen actions, and these overestimation errors can cause the algorithm to produce bad values. And the cause of this overestimation really is distribution shift, because your pi beta is not equal to the learned policy pi or the argmax policy for the Q function.